So let me, while she's doing that, let me define what it means to be a Euclidean domain. Okay. So here's a definition. Okay. So let R be an integral domain. Okay. So an integral domain is a unital commutative ring that does not have any zero divisors. Okay, no zero divisors. So we say, right, that R, okay, is a Euclidean domain. Okay. If R, okay, has a function, okay, and we call it the function d from R to, say, z greater than or equal to 0, union minus infinity. Okay, this is a little strange. Okay. Okay. Such that the Euclidean algorithm holds. Okay. Such that, okay, for all a and b, okay, in R, okay, with b not equal to 0, okay, there are q and r, okay, in R, such that I can divide, okay, b into a, bq plus r, okay, right, with the understanding that, see, this d is called a measurement function, okay? Thank you. It's called a measurement function. So what we want, okay, is for d of r to be less than what? Anyone? D of b, right? D of b. Okay, so that's what you want here. Okay. So this is called a Euclidean domain if it has a function like this. Okay. So note that z, okay, is a Euclidean domain with d of the function, I don't know, I need a letter, c equals the absolute value of c. Okay, that's how you measure things. Make sense? Okay. And to the degree, and fx, okay, is a Euclidean domain, okay, with what is the d? How do you measure how do you measure the size of a function? By its degree. Good. Okay. Right, which can be negative infinity if g is if it's 0. Let's go back to the thing that I asked you to finish up. Okay. So so Shuang is trying to prove that every ideal in Z is a principal. Every ideal is a principal ideal. Okay. So the idea here is that I start with an ideal. I want to show that it's principal. Okay. So suppose it's non-trivial. Non-trivial, then let A be the least positive number in I. Note A exists because I greater than, what does this say? Do you mean Z? Yeah, Z greater than or equal is well ordered. I don't know. We haven't discussed this term, okay? But it just means it has the smallest element, okay? We want to show that A generates I. Okay. So clearly A belongs to I. Okay. That's because I is an ideal, A is in I. This symbol right here we know is the set of all things that look like that. Right? We saw that. So that I gobbles up everything. Let N be an I. Then there exists Q and R such that N equals QA plus R. Okay. With what? With R less than what? With R between 0 and an A. Okay? So, squeeze me? So, note that A equals R equals N minus QA. Okay, so N is an I because we said so somewhere. And then Q A is an I because A is an I, so this guy is an I. So now R is an I, right? But R, right, has to be, well, you don't have to contradict anything, right? So you can get rid of this piece right here So R, right, is a positive object which is less than A. Well, it's a non-negative object that's less than A, right? But the smallest positive object which is an A is, I'm sorry, I, is A, right? So since R is smaller than it, okay, then R has to be 0, okay? So by the minimality of A, let's keep this, okay? So by the minimality of A, okay, we have this. So N equals QA equals, yeah, okay? Everybody okay with that? So, all right, so here's an example of something. These two things are important because they have the Euclidean algorithm. Now, how do you prove that something is not a Euclidean domain? Yes?
You find an example of something where you can find just one expression of A in that form.
So what does it mean to be a Euclidean domain, right? You have a function, right? So to prove that you're not a Euclidean domain, you prove that you have no function. But having no function is a very, very difficult thing to prove, right? Because you basically have to go through every function on Earth, right? And then show that it doesn't work, right? So in general, the examples that we have are very, very slim, okay? But I'll show you a way of doing this, okay? Alexi?
I'm sorry, the examples we have
are very few of things that are not Euclidean domains, okay? No, I'm sorry. Well, let's continue. Okay, so here's a definition, okay? So we say, okay, an integral domain is a principal ideal domain, okay, or a PID, okay, if every ideal, okay, is principal. Okay, then what does it mean to be principal? Principal means it's generated by one object. Okay, so every ideal, okay, is basically all the multiples of a particular object. Okay, so for example, okay, what we showed here is that Z, okay, is a PID. Make sense? Okay, so it's not hard to imagine that, like here's a statement. Okay, if A and B are in Z, okay, then the ideal generated by, this is a terrible notation, okay? Then the ideal generated by A and B, say, written unfortunately, right, like this. This can mean anything, right? In this case, it means the ideal generated by A and B. So what would this be? So for example, if I have like 25 and 20, right? The ideal generated by that is 5, right? So what is this given by? Unfortunately, this symbol is not great either. Okay, so it looks like this. Does it make sense? So so for example, this guy equals 5. If you have a whole bunch of them, right? If you have A, B, C, D, E, F, G, then it's just GCD of all of them. Alexi, is that okay? Right. So now what I want to claim, okay, is that every Euclidean domain, okay, is a PID. Okay, so if I have this, then I have that, and so I automatically know that all of those polynomial rings are. I need a piece. Where's the eraser? All right, so here's a proof. Okay, so let R be a Euclidean domain, okay, and let I be an ideal, okay. If I is trivial, okay, then I is simply generated by the 0 element. Okay, so we're done there. Otherwise, okay, so what are we going to do now? Okay, so what does it mean, all right? What does it mean here, okay, to be Euclidean domain? I guess I should be very specific here. I guess the only object that I'm allowing to go to minus infinity is 0, okay? So It doesn't have to go to minus infinity, right? But it can, right? So obviously here, it doesn't go to minus infinity, but the only object, right? Perhaps. Well, how do I say this, right? So I'll figure out a way to say that later. Huh? Yeah. With d of r minus 0 completely contained in, right? It's like, I'm sorry, okay? The only thing that's allowed to go to minus infinity is 0, okay? All right, so otherwise let a, right, be an I, okay? Okay. Now, what can I say about this object right here? Okay, let A be an I, right? Be an element, okay? And what do we want to know about A? We want to identify A, okay, with a minimal, okay, positive d value. It doesn't even have to be positive, minimal d value, non-negative, non-infinity. You know what I mean? Okay, minimal d value. Okay, so what I want to do, right, is I want to find something. I want to find a generator, right, for I. Now, what's going to generate I? Something small is going to generate I. What do I mean by something small? Okay, well, I have to have a measurement to know what is small, but aha, I have one. So I'm going to pick the d with the smallest z value, d value, right, inside this ideal. Does it make sense? Okay. So then we claim, okay, that I is generated by A. Make sense? Same proof. Okay. Now, clearly, right, one direction holds. This is just the same as Schrödinger's proof. Okay. So let n be an element. Let's use a different letter. Let s be an element of I. Then what do we want to do with s? Okay. Yeah, Phyllis?
So there exists Q and R
Right.
in R.
R, right. Such that.
S is equal to AQ plus R.
Good.
With dr smaller than dA.
Good. Okay. But then, right, then what do we know about R? R is equal to S minus QA, right? But what do we know about S? Okay, S lies in I, and A lies in I, so this whole thing lies in I. So this guy lies in I. Does it make sense? Okay, I guess I should say that this guy is non-zero, a non-zero element. Okay, right? So now I've got something with smaller d value, okay? By the minimality, okay, of A, what do we know? A is the smallest thing in I. Now I have something smaller in I. So it has to be 0, right? Okay, i.e. S is QA, which is an I. Okay. Make sense? Sheridan, is that okay? Yeah, okay. All right, so every Euclidean domain is a PID. Okay. Today we're going to learn a lot about different kinds of ideals. Okay. So that's what a principal. That's something about principal ideals. Okay. Now, here's an example of a bad situation. Okay. So we know, okay, that Zx, okay, does not have long division, okay, in the way that fx does. Everybody agree? Okay. So here's an example. If I were trying to compute this thing right here, right, I wouldn't be able to move on. Okay. Does that mean that it's not a Euclidean domain? Does this itself tell you that it's not a Euclidean domain? No. Okay. Why not? Because there might be some other kind of long division, right? There might be some other function, okay? So the question is there some other, okay, measurement function, okay, for z, okay, for which, okay, z x comma d, okay? So this is just a notation for, I have a measurement function on here, okay, is a Euclidean domain, okay? And the answer is no, right? And how are we going to show that? We show that it's not a PID, okay? So here's a claim, okay? So many of you might have seen this before, okay? In a sense, this is kind of all review still, okay? So the ring, okay, Zx, okay, is not a Euclidean domain, okay? And is not principal, let's see. Not a PID, and thus, okay, not a Euclidean domain. All right, so in order to find a reason why this ring is not a PID, we have to find an ideal, which is, which is not principal, okay? So we claim, okay, that I equals, okay, is not principal. Does anybody know which, this is a classic object. If you're not Alexei, do you know? Do you know? Huh? You have to, it's generated by two objects. 2 and x, good. 2 and x. Right? So these are all the objects that are generated by 2 and x. Okay? So for example, okay, so this set, right? Okay, I, okay, is this ideal I, okay, is of the form, okay? Remember that if I have one object, okay, then I is the set of all possible multiples of A, right, by elements in R. Okay? Here, okay, as you'll prove on the homework, number whatever, 10, this is all the possible linear combinations of objects. Okay, so it's 2A plus xb, okay, where A and B are where? Not Z. What is my base ring? Not Z. Zx. Right? Okay. Yeah? Phyllis, is that okay? So it's all things that look like that, right? Does that make sense? Okay. So let's take a look at this, right? So, so why isn't this ideal principal? Okay. So suppose the sky were principal. Okay. Suppose I were principal. Okay. I.e., I is equal to C for some C in Phyllis. Zx, good. Okay, Zx. Okay. So what does this mean, right? So C belongs to 2 comma x. Okay? Right? Well, okay, so what does this say? So I'm sorry. So what does it say? So that means that 2 belongs to I, right? So 2 belongs to this, okay? And x belongs to this. Is that clear? Okay. What does it mean for 2? So have we talked about divisibility in this class? I can't even remember. Okay. If 2 is an element of this, that means that 2 is a multiple of C. Okay? So that means that C divides 2. Okay? So C divides 2. Okay? And also C divides x. Is that clear? Right? So C, right? So here, 2 is a multiple of C, x is a multiple of C, right? So this happens. Okay. What kinds of things in Zx? We're in Zx right here, okay? So what kinds of things divide 2? What divides 2? 1, 2, minus 1, and minus 2. Okay, so the only things that divide, so therefore, right, what are the possible choices, okay, for C? Okay, so C, okay, so C has to divide both, it's either in here, okay, or, and it also divides X. What are the things that divide X? X minus X, 1 minus 1. Okay? So C can only be 1 or minus 1. Okay? But then, okay, if I have 1 or minus 1, right? If C is 1 or minus 1, remember C is now a unit, okay? It has a multiplicative inverse. What happens if I have a multiplicative inverse? What is this thing right here? Z adjoint, it's the whole thing, right? If you're generating 1, right, you get Zx. Now, why can't it be Zx? If you look at this guy right here, okay, look at this object right here. What polynomial is excluded from this set? The 1 polynomial. You can never get the 1 polynomial out of this arrangement. Does that make sense? Okay? But 1 is not an I. Okay? So we have a contradiction. So we have a contradiction. What did we contradict? We contradicted the fact that this guy was principal. Okay? So here's an example of something that's not a Euclidean domain. Okay? And because it's not a Euclidean domain, we rarely talk about this object in Galois theory. Okay? So Galois theory, okay, you might think is kind of boring, right? Because it only deals with these two kinds of objects, right? Okay. But it's kind of amazing how much structure there is here. Everybody okay? All right. So today I want to talk about two different kinds of ideals, okay? Prime and maximal ideals. Okay. So here's a definition. Okay. Let R be an integral domain, okay? And let I, okay, be an ideal, okay, of R. We say, okay, that, okay, R is a prime ideal, okay, is prime if for all A, B, oops, sorry, not R, I, okay, for all B in R. Let's start it that way. Anybody remember the definition of what it means to be prime? Not Alexei. Okay, good, I'm not reviewing stuff. Alexei, okay, if
It's prime if A, B, and I implies A and I or B.
okay, then A is an I or B is an I. Okay, so how do I write this down? Okay, so I is prime if for all A, B in R, okay, A, B, and I implies that A is an I or B is an I. Okay? Does that make sense? Okay? So that means when you ever have a product, okay, that's being sucked into I, then one of its components has to be an I. Okay? So what does it mean to be an integral domain? The zero ideal is prime. Okay? So, okay, here's a claim. Okay? Right? Let R, okay, be a ring, okay, then R, okay, is an integral domain if and only if the zero ideal is prime. Is it okay? Yeah? Are you all right? Is everyone okay? Right. So the proofs work the same way on both sides. So I'll do one direction and you can do the other direction at home. Okay. So suppose that R is an integral domain. Okay, I want to show that this guy's a prime ideal. Okay, so how do I show that this guy's a prime ideal? Okay, I want to prove that I have this situation right here. Okay? So my word next is let A and B be in R. Okay, and suppose, what do I suppose? AB belongs to this ideal. Okay, i.e. AB is equal to 0. Make sense? Okay. But I'm an integral domain, right? So therefore, A equals 0 or B equals 0. That is the same thing as say that either A is in this ideal or B is in this ideal. Done. Got you? Is that okay? All right. So I just want to make sure you do this split direction. Okay. So we know that, let's look at Z. Okay, let's look at Z. Okay. So here's a claim. Okay. In the ring Z, okay, an ideal, okay, I, now we know that I is principal, so it has to look like something like this. Okay? This guy is a prime ideal if and only if what? A is prime. Good. Okay, it's prime. Make sense? Okay. All right, so let's try to prove this. Okay. All right. Okay. So suppose, okay, let's go this direction right here. Okay. Suppose that A is prime. Okay. And let, say, Q and R be in R. And what do I want to know about QR? Q, comma, R. So I'm going this direction. I want to show that this guy is prime. Okay? The Lord? Yeah, I want to show that, I want to assume this. Make sense? Okay. Now, so this means that QR is a multiple of A, right? So that means that A divides it, okay? So A divides Q times R. Now, A is prime. What is a basic property of a prime dividing a product? Then A divides Q, or A divides R. Right? And what does this say? So when I write division and when I write inclusion, you see that the notation flips. So the smaller thing, okay, the smaller thing slashes the bigger thing, but the bigger thing lies in the smaller thing. Right? So if I want notation to flip, I have to write that. Yeah, okay. Or R is an element. Make sense? Okay. Now let's prove the other direction by contraposition. Okay. So suppose that A is not prime. Okay, i.e. A is equal to B times C, where B and C are both greater than or equal to 2. Assume A is positive, okay? Positive. All right, now what? Okay, I have to violate this condition right here, okay? I have to show that this guy is not prime. How do I show that something is not prime? I have to find A and B. I have to find two things whose product is an I. Can I find two things? Simona, what are they? B and C, okay? So then, right, BC lies in A. I mean, it is A, right? So it certainly lies in A. But what do you know? What do you know about B? B is too small, right, to be in A, this A. Is that what I'm trying to show? Yeah. B doesn't lie in A, right? Because in order for B to lie in A, B has to be a multiple of A. But A is a multiple of B, right? It's the wrong way, right? And C is not. Right. Everyone okay with that? Lauren? Okay. All right. So, so I is not an ideal. It is not prime. Everyone okay with that? Okay. So this is called the prime ideal theorem. Okay. The prime ideal theorem. Okay. Okay, the prime ideal says the following. Okay. Let R be an integral domain, okay, with P, an ideal P. Okay? So when we talk about ideals that are about to be prime, we call them P. Okay? Okay? And why do we call them prime? We call them prime exactly for this reason right here. Okay? This is why we call them prime ideals, because they behave like prime numbers. Okay? All right, with an ideal P. Then, anybody know the statement of the prime ideal theorem? Yeah, our quotient P, right, is what? Is an integral domain if and only if P is prime. Make sense? Okay. All right, I'm going to do one direction, and you can do the other one. Alexi, forward or backwards? Forwards, okay. All right, so suppose, okay, that R mod P is an integral domain. Okay, so this will give us some practice operating in the universe of quotients. I want to show that P is prime, okay? So I want to start out with two objects, okay, in my ring, okay? And I want to suppose that their product is in P. Make sense? Okay. Now, what am I going to do with these two objects right here? Okay, so I'm going to go into the world of quotient land, right? So if P, A, B is an element of P, then what can I say about this object right here? It's a zero element. Okay, it's a zero element in R mod P. What is the zero element in R mod P called? Well, okay, it's called 0 plus P. Okay? Does that make sense? Or it's just called P. Does it make sense? Remember that the zero element, okay, in here, so if you're in P, then A, B plus P is P. And these are the zero elements. Now, how do I factor the left-hand side? Okay? So it becomes A plus P times B plus P equals P. Okay? You see where we're going with this? Now I'm in a universe of R mod P, right? But R mod P is an integral domain. And this guy is the zero element. So Simona, what happens? Okay, so A plus P equals P, or B plus P is equal to P. Okay? But what does A plus P equals P? A plus P equals P mean? Huh? That A is in P. Okay? So either A is in P, okay, or B is in P. Right? And that's what it means to be an integral domain. Okay? So I want you to do this next direction, this direction. Okay. It's exactly the same, it just goes backwards. Okay. So let's talk about this other ideal. Okay, here's a definition. Okay, so here's a new notation. Okay, here's a notation. Let R be a ring. Okay, and let I be an ideal. Okay, and let A be an element of R. Okay, so I have three objects. Okay, I have R. Okay, I have I, and I have A. And A could be inside or outside of I. Okay. Then what do I mean by this object right here? crappy notation. Huh? It's the smallest ideal that contains both I and A. Okay? It's the smallest ideal that can, so it's this ideal right here called J. Okay? So then this guy, right, is unfortunately, okay, the notation is awful, okay? So so J is an ideal, okay? I is contained in J, and A is contained in J. Okay? So it's the, everybody okay with that? Okay. Now, here's a good guess, okay? IA, what do the elements look like of IA? Yeah? RA plus B, where? B is in what? No, yes, okay. B is in I. R is in R, good. Okay. So it just looks like this, right? Okay. It just looks like linear, it just looks like, if you think about linear combinations, right? It just looks like RA plus CI, whatever that means, right? Okay, but CI is just C because I absorbs everything. So it looks like RA plus I, which is this. Okay, so you should take a look at that, check that. Okay. I want to talk about what it means to be a maximal ideal. Okay. Okay. So let R, okay, be an integral domain, okay, and let M be an ideal. Okay. So we say that M is maximal. Okay, so here's the idea. Here's R, and here's M. Okay, what do I mean by a maximal ideal? Huh? Say that again?
If we add one more element.
Yes, that's right. Okay, so how do we say that? If, okay, for all, what are we going to add? A. Where's A? Yeah, so A is an R, but it's not an M. Okay, we have the following. Okay, so if I take M and I shove an A, right, and I generate, I'm going to get all of R. What's the difference between saying that something is maximal and saying that something is maximum? Huh? Maximum is unique, okay? Maximum is unique. So for example, if I have like a family tree, right, where you have, I don't know how to draw a family tree. Here, let's draw a tree. Okay, so here's an example of a tree, right? Okay, these four objects are maximum. Maximal. Okay, maximal means that there's nothing on top of it. Okay, there's nothing on top of it. But this one is not, so maximum means that you're bigger than everyone else. This one is not bigger than that one. Okay, so these guys are not maxima. Okay, they're not maxima. They are maximal because there's nothing on top of them. Okay, that's what this means. Okay. All right, so that's an example. So here's a claim. Okay, let P in Z be prime. Okay, let's just make it positive. Okay, then this guy is maximal. Okay, in Z.
So I think M should not be R.
Huh?
M should not be R.
M should not be R. Ah, that's true. Be a proper ideal. How's that? Good, thank you very much. Okay, so here's the proof. Okay, so Okay, so I want to show that this guy is maximal. So what do? I pick something that's not in it. Okay, so let A, okay, be in Z minus P, like this. So A is not a multiple of P, right? But since P is prime, what can we say about A? Something stronger that we can say about A. It's relatively prime to P, right? If you're not a multiple of a prime, then you're relatively prime to that prime, okay? Then the GCD, okay, of A and P is equal to 1. Therefore, okay, right, there are M and N, okay, in Z, okay, by the Euclidean algorithm, such that AM plus PN is equal to 1. Is everyone okay with that? Now, let's take a look at this. Now, blah, 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 blah. I shouldn't use the letter M, but okay. So what do I know? So I want to look at this ideal right here, which is generated by A and P, right? Okay? So this guy is in there, and this guy is in there, right? So their sum is in there, okay? Contains, okay, AM plus PN equals 1. Okay? So now you've got yourself an ideal with a unit in it, okay? So what do we know about this guy? Okay, this guy is all of Z. Okay? So what does that tell us? That P is maximal. Is that clear? Okay. Okay. So let's talk about the maximal ideal theorem. Okay. So here's the claim. Okay. So let M be a proper ideal of an integral domain R. Okay. Then this is called the maximal ideal theorem. Okay. So what am I about to say about R mod M? It's a field, okay, if and only if M is maximal. Good. Make sense? Okay. All right, so again, I'm going to prove one direction. Let's prove the backwards direction since I did the forwards direction last time. Okay, so suppose that M is maximal. Okay. Now, I want to show that this guy is a field, okay? Right? Now, a field has lots of different properties, okay? And I pretty much know what all of them are, okay? I mean, I pretty much know that R mod M satisfies all of them except possibly one, okay? And that is that it has multiplicative inverses, okay? So suppose, okay, now I have to choose an object, A plus M, okay? I have to choose an element in here, but I have to make sure that this element is not. There's one object in here that I don't really want to have a multiplicative inverse, and that is the 0 element. Okay, so what is the 0 element in here called? What is it called? M, okay? So this guy is not M, okay, in R mod M. Does that make sense? Okay. So what does this mean? Huh?
A is not.
Yeah, so A is not an M, okay? But M is maximal, okay? Therefore, the ideal generated by M and A is equal to R, okay? So in particular, okay, 1 is an element of here. You see where we're going with this? Okay? Now, since 1 is an element of here, and here, right, looks like elements of this type, okay? So there are, okay, so I need 2 letters, right? One which lies in here, and one which gets multiplied by this, okay? So there are M in M, okay, and R in R, such that, yeah, Lexi? AR plus M is equal to 1. Yeah? Nikki, what should I do next? I need to get back into this. So remember, I'm trying to get back into this world right here. Okay, so what do I need to do to both sides? You want to, anyone? You want to add add a big M, right? So therefore, so AR plus M equals 1 plus M. Tell me about this object right here. Huh? I took a quotient. No, I M-ified. Yeah, I took the quotient. Now what? Well, what about this M right here? It goes away. Okay, this M goes away because it gets sucked into that M. And then here I have AR plus M. Okay, so I have A plus M times 1, M plus M, R plus M is equal to 1 plus M. What have I just done? Okay, I have found myself a multiplicative inverse for A plus M. Isn't that cool? Okay, so A plus M has an inverse. Okay, so you do the opposite direction. I love being able to say that. You do the other direction. That means I trust you because you guys are brainy. Okay, everybody have a question? So here's a cool idea. Okay, here's a claim. Okay, right. Let R be an integral domain, okay, with an ideal I. If I is maximal, then I is prime. So all maximal ideals are prime. Got it? Huh? Yes? Are you happy? Okay. All maximal ideals are prime. Okay. Let's talk about y. Okay. Let I be maximal. Then what do you know about R mod I? Is a field, but all fields are integral domains. So R mod I is an integral domain. Yeah? Therefore, so I is prime. Hooray. Okay. The other direction is not true, okay, en general, all right? So I believe that this guy right here, okay, is maximal, right? But it's not prime, okay? So note, okay, the converse is false. Okay, think 2 comma x in Zx. Okay, this guy turns out to be maximal, okay, but this guy is not prime. There's one way to make the backwards work. Anybody know what it is? No. Nope. Something about R. Okay? It turns out that if R is finite, okay? If R is finite, the backwards works. Because if you have a finite integral domain, it turns out to be a field. Okay? So here's a note. Okay? Okay? If R mod I, okay, is finite, okay, then the converse holds. There's a homework assignment, right, that says something about that. Yeah, okay. Okay, so let us understand how to think about various types of things, okay? So what I want you to do, so we're going to look at the following. We're going to look at rings. Here's a rings, okay? And then I have an ideal, okay? And then I want to look at the quotient, okay? And then I want to ask if it's maximal, if it's prime. Maximal, prime. Okay, let's take a look at this right here. All right, let's take a look at Zx, just for giggles. Okay, Zx. I want to know about the ideal this. Okay? So I want to look at the ideal this. Now the quotient is equal to this. Okay, now let's think about how to render that. Okay. Basically, this is saying I am taking z of x. These are all polynomials in z. But I'm dividing out by x. What does that mean? That means that every time I see an x, what do I do with it? I cross it out. What am I left with? I'm left with just z. Okay? What kind of object is z? It's an integral domain, which is not a field, right? The last time I checked, z was not a field. Okay? So do you see that? So you're immediately able to say that this ideal is maximal, not maximal, but it's prime. Now, if it's not maximal, then something's bigger than it, right? What's bigger than x? X2. Huh? X2. X2, right, excellent. Okay, so let's take a look at 2x. Okay, so now I'm taking a look at x here, and then so every time I see a 2, I kill it. Every time I see an x, I kill it. What am I left with? Z2, 0 and 1. Those 0 and 1 are the only things that survive, right? What do I know about Z2? Well, yes, Alexei? It's a field, right? And we know that. So yeah, does that make sense? Right? What did I think I said some garbage over there. Did I mean this? That's what I meant. Okay, this guy is prime, but it's not maximal. Okay, everyone see how this works? Okay, so what about something like, I don't know, we're going to get to this in a little bit, but what about something like this? Okay, now that's a little bit weird. Okay. Okay, what does this say? Yeah. So that says that every time I see an x minus 2, I put a 0. That is the same thing as saying that every time I see an x, I put a 2. You see that? Okay? Now, if I take zx, and every time I see an x, I put a 2, what do I get? I get z, right? But it's a different z than the top z. Do you see this? This one is a little bit different than that one. It's weird, right? They're isomorphic, right? But the idea is a little bit different. So this guy is still z, right? Okay? So this is not a maximal, but this is prime. Okay. What about something like this? Let's say qx. Let's take qx. Okay. Now everything here is maximal. I'm sorry. What am I meaning to say? Everything here is principal. Okay. Everything here is principal. So suppose I mod it out by x itself. Okay. So what is qx mod x? Is what? It's just q. What do we know about q? It's a field, right? So this ideal is both maximal and prime. Okay. What about something like 2x? What can I say about 2x? Yes. 2x is the same thing as x. Does everyone see why? 2x is the same as x. See, because x is a multiple of 2x, and 2x is a multiple of x by multiplying by 1/2. Okay? So these two things are actually the same. Okay? So this guy mod out by 2x is still isomorphic to q. Okay? Is everybody okay with that? Okay? But what about something really weird like this? Okay? This ideal right here. Okay? So what do I know about this? So qx mod out by the 0 ideal is qx. What kind of object is qx? Is it a field? No, it's not a field, right? Certainly not a field. So this is not maximal, right? Is it an integral domain? Yes, it is, right? This is. So this guy is prime, right? We know this is prime because in order for this to be prime, this has to be an integral domain, right? So everything's OK. Everybody clear about that? Let's add one line right here. What about f? F. OK, f. What can we say about f? Well, there are only two ideals of f. Everybody OK with that? So let's look at the zero ideal. OK? Your contact falling out. OK, so what is f mod 0? F. OK? And what is f? It's a field, so it's maximal. OK, and it's prime. Now, why is this maximal? This looks a very small object to be maximal. The only other ideal is the whole thing, right? So clearly this guy is maximal. So it's really weird to think of the zero ideal as being maximal. But that's because in a field, there's nothing bigger than it. Make sense? OK, so everybody know how to manipulate these objects like this? OK. Any questions? All right, let's talk about the fundamental theorem of ring homomorphisms. OK, let's talk about the fundamental theorem of ring homomorphisms. So suppose I say, I want to create this isomorphism. OK, so here's the goal. OK, create the isomorphism. OK, given by zx mod x is equal isomorphic to z. OK, using the fundamental theorem. OK, everybody understand? Now remember that the fundamental theorem, okay, states the following, okay, that if what? If phi from R to S is a ring homomorphism, then phi prime from R to the kernel, R mod the kernel of phi, okay, to the image of phi is a ring isomorphism. Yeah? Everybody OK with that? So this, right, this is the end product that I want. OK, so I have to feed in. This is the phi prime, right? OK? And I want a phi that generates it. OK? What is the phi? Well, can someone give me an example of a phi? Consider phi. OK? And what is my R in this problem? Zx, right, Zx. OK? If I want something like a quotient as an output, then my input has to be just the numerator. And what is my output? Yeah, just get the sets. Let's get the sets right. No? What do I want? What's S in this problem? It's that one right there. Okay. Okay. Now I'm not done. I have to tell you what the function is. Okay. Be given by. Okay. So I get to put in a polynomial, say f. Okay. I have a polynomial. I need to generate an integer. How do I do that? Huh? You take the degree. The degree, right, is not going to. It's not going to be a homomorphism. Okay, not going to be a homomorphism. Huh? Take the constant. Yeah. What's another way of saying take the constant coefficient? Evaluate at 0. Okay. Evaluate at 0. Good. Okay. Right? Does that make sense? This guy is a homomorphism. Okay. Katya, do you see what's going on? Okay. Okay. So here, okay. So let's take a look at this function right here. Okay. Now the kernel, okay, of phi is the set of all f's, okay, in Zx such that f slash c is equal to 0. F slash 0 is equal to 0. Okay. So does that make sense? So this is exactly what Simona said. If you take a polynomial and you fill it with 0, all you get is the constant coefficient, right? And if you're insisting that the constant coefficient is 0, then what you're going to get is a polynomial with no constant coefficient. And what can you do with a polynomial with no constant coefficient? You can factor out an x, right? So this guy is given by this. Is that clear? Okay. Now, what is the image of this? Okay. Okay. So I claim that the image is z, right? So this is not a difficult problem. Okay. Let a be in z. Okay. I want to prove that phi is surjective. What polynomial goes to a? A. Okay. Then phi of a equals a. If you take a, right? Everybody okay with that? Right? So the image, okay, of phi is all of z. Okay. Therefore, by the fundamental theorem, I get zx mod x is equal to z. Does it make sense? Okay. All right, let's take this idea, kind of run with it a little bit. Okay. Okay. So consider the following. Homomorphism. Okay. So I'm going to take phi. I'm going to start with an element in qx, a polynomial in qx, but I'm going to spit out an element of c. Okay. This is a little bit strange, but let's think about it. What I want to do, okay, is the following. Okay. F, okay, phi is going to take a polynomial f, okay, and I'm going to slash the square root of 2 inside. Ugh, that's weird. Am I allowed to do that? Okay, after all, right, f is a polynomial in qx. Am I allowed to stick in, right, root 2? Well, why not? Because this guy is actually in cx. Okay? So I can take this f, okay, I can treat it like a polynomial over c, and it can stick in root 2. Make sense? Okay. Now, this problem gets a little bit weirder, okay? So what do we know? The kernel, okay, the kernel of phi, okay, is an ideal in qx. Yeah? The kernel of phi is an ideal of qx. Okay? So this ideal is, the kernel is, what kind of ideal? Is? Does the p? Principal. It's principal. Okay? So the kernel is principal. Okay? So phi, so let's just say, so the kernel of phi, okay, is equal to the set of all things, right? Right? Is a set of all things such that f of root 2 is equal to 0. Okay? And this is generated by one object. And why? So what are some polynomials that kill root? So this is killing, right? Okay. So let's name a polynomial that kills root 2. How about this one right here? That kills root 2. Is that in the kernel? Why not? Because this guy has to be in qx, right? Okay. So this does not have coefficients in q. So this guy's not in the kernel. Okay. What is in the? Can anyone name something that's in the kernel? X squared minus 2. So x squared minus 2 is certainly in the kernel. Does it make sense? Okay. Anything else in the kernel? What other things are in the kernel? Multiples of x squared minus 2. Okay. Any multiple? Anything else that's not a multiple of this? Okay. So here's my claim, right? So this guy right here is that. Does that make sense? No? Yes? Okay. So the question we want to ask is, we think, right, that the kernel of phi equals x squared minus 2. Okay. Can we prove it? Okay. So we'll do this tomorrow. Okay. What is special about x squared minus 2 that allows it to be the answer and not something else? Okay. Now what is the image? Okay, what is the image? Okay, so let's think about what the image of phi is. Okay, so let's take a polynomial, right? Phyllis, give me a polynomial. X squared plus 1. Okay, what is phi of x squared plus 1? Okay, right? Right? This is x squared plus 1 slash root 2, which is 3. So give me something else. Give me a function that's not x plus 1. Okay. So this is x plus 1 slash root 2, which is 1 plus root 2. Okay. If I tried to do something crazier, like x cubed plus x squared plus 2x plus 1, right, then I would get root 2 cubed plus 2 plus 2 root 2 plus 1, which is, that's a 2 root 2. That's a 3 plus 4 root 2. Yeah? Okay, do you have a guess? You have a guess? The image of phi looks like the set of all numbers of what form? Remember that these can be divided by 3 and 7. And what does it look like? A plus b root 2, a, b, and q. Good. Okay, so that's our guess. Okay, so tomorrow we're going to assemble, okay, what we're going to do is we're going to, it's going to be obvious what we think it's going to be, right? But we're going to try to assemble the isomorphism that this homomorphism gives us, okay? And the answer, anyone tell me the answer? We've written the answer down on the board, okay? It's qx mod out by x squared minus 2 is isomorphic to this guy right here, which is called q root 2, okay? So tomorrow we're going to be generating this object right here.